Okay, good morning. Welcome to video 12-1. Today we're going to be talking about the triangle proportionality theorem. So first let's talk through the theorem itself that we see here. I'm on page 632 and explain one in your textbook. And it says, as you saw in the Explore on the previous page, it talked about doing a triangle proportionality theorem set up by creating it with constructions with the compass and a straight edge. We obviously didn't do that, but I want to walk you through what the triangle proportionality theorem says. And it says that if a line parallel to a side of a triangle, so here's the third side that we talked about with the triangle mid-segment theorem, remember? The line went across right in the middle, and we had that the mid-segment was half the length. We're no longer talking about the lengths of those segments, but we're talking about how this line that cuts through the triangle, and notice they've purposely drawn it so that it is not going right through the middle. See, this piece here is not half, or this E point is not the midpoint. So AE and EB are purposely not drawn like they look the same. So basically, if we have a parallel line to that third side that cuts through a triangle at any point, then it divides those sides, meaning AB and AC. It divides those sides into proportional pieces. And it's really easy to set up the proportion, you guys. You can literally draw the proportion over here and set it up in the same way you visually see the diagram. So AE is above EB in the fraction, AE is above EB. AF is above FC, and again, AF is above FC in the fraction itself. So just a reminder of what you need to remember, though, is that it's no longer small triangle to big triangle, but that parts of the triangle are proportional. So now what we're going to do is we're going to actually go through and figure out why that theorem holds true with some knowledge that we have about similar triangles from before. So if we zoom in here a little bit, for example 1, so we're given the diagram with triangle ABC over here on the right, and we can see that triangle ABC has been cut through by a line that is parallel to that third side, and that really, you guys, is the only given that we have to go on in this proof. What our goal is to prove the triangle proportionality theorem. That means, given that we have a parallel line cutting through the triangle, prove that the parts are proportional. So, here's how we do that. The first step is to show that we do have similar triangles to begin with, and we can set up a proportion with the similar triangle pieces. So, because we know that we have parallel lines here, we're going to be able to conclude angle 1 and 2 and angle 3 and 4 are congruent angle pairs, not necessarily congruent to each other, but that 1 and 2 are the same, and that 3 and 4 are the same, because if we think about this line AB right here as a transversal cutting through those parallel lines, then those, you guys, are corresponding angles. So that's the corresponding angle, and remember we had changed that in one of the first modules of our book to a postulate. Sorry, it's hard to write with this stylus here. So what we can say is that if we have two angles that are congruent because of those parallel lines, then our triangles are similar by our angle-angle similarity theorem, which is one that we learned in the last module. So now we're going to go to the next page and continue this proof on page 633. And the rest of this proof starts us where we are talking about the similar triangle proportion. So that's the whole small to big thing that we're doing up at the top. And then throughout some steps with some algebra, we are going to be able to get to that the parts are proportional at the end. So for step 2, we're going to start by saying what is AB over AE equal to, and actually what they did there is they started with the big length for AB on the top to the small length from the triangle as you see on the previous page. So AB is the whole length of the left side over AE is just the top part. So we're going to say that's going to be proportional to the whole length of the right side, which is AC, over AF, which is just the top part. Let me zoom in a little bit here. Make it a little easier to write. Okay, so we have AC over AF. The next thing we're going to do is to talk about not only are corresponding sides proportional, but the length AB is actually made up of two smaller pieces, the top piece plus the bottom piece. So that's what we're going to do with AC as well. We're going to split it into its top piece, which is AF, plus its bottom piece, which is FC. And all of that is still over the original denominator AF. So again, that's the segment addition postulate. We're just breaking the whole length of AB and AC into the pieces that make up the whole length. Then what you can see is, on the left-hand side, this becomes just 1 plus EB over AB here. The way that they did that is that they divided AE into each piece of the numerator. They divided AE over AE and got 1, and they divided EB over AE and got that remaining fraction. So I think you can see the same pattern happening above here. AF over AF is going to become 1, and then the second fraction is just FC over AF. The next step, they tell us to subtract 1 from both sides, and so we are simply left with FC to AF. And then to get back to what it is we're being asked to prove up here, notice we have the proportion, it's just flipped. So if I take the reciprocal of both sides, then I am where I wanted to be, which was AE over EB equals AF over FC. So again, we moved from knowing that corresponding sides of similar triangles are proportional to not just is that true, but the parts of the sides of the triangle are proportional as well. So that's the first part, proving that proportionality theorem. As we go down to explain 2, a little further down the page here, now we are going to be using the triangle proportionality theorem to find the missing lengths in the pieces of our puzzle here. So walking through example 2, this is pretty straightforward setup. We are going to find CY. You can see that that's missing on our diagram. We're given that in the diagram we've got parallel sides there, or a line cutting through the triangle parallel to a side. And so we can set up with the triangle proportionality theorem all the pieces that we know. So we know AX is proportional to BX, and AY is proportional to CY. And so we're substituting all the things that we know from the diagram, 9, 4, and 10, into the places that we have. CY is the only remaining piece. And then it says take the reciprocal of both sides. That's to put the variable that you're solving for in the numerator. It's really not a necessary thing to do that if you simply cross multiply at this point. You're going to get 9 times CY equals 40. And if you divide by 9 right here, then you can go straight to your answer of CY is 4 4/9 or 40/9. So just so you know, the steps of take the reciprocal of both sides and then multiply both sides by 10 are all basically going to be accomplished if you simply cross multiply. Okay? So in part B, we're filling in and we want to find BN in this new diagram. Excuse me, we want to find PN in the new diagram. So let's fill in what we need to here. Now that we know that PQ and LM are marked parallel, then we know the pieces of the triangle's sides are proportional, and that is NQ is proportional to QM, and also NP on the left-hand side there is proportional to PL. Now you notice NQ and NP are the same part of the side, meaning they're at the top. So we want to put them in the same part of the fraction, the numerator. Then QM here is in the same side as well. So notice that the location matters as we set up the proportion. PL and QM are there, and so QM and PL are in the same part of the fraction as well. Keep that in mind as you set up your own proportions here in the your turns next. So we're going to substitute what we know. We know NQ is 5. We know QM is 2. And 3 is going to get substituted in for PL. And we're left with the proportion you see below. 5/2 equals NP times 3. And again, if you cross multiply, we're just going to have 15 equals 2 times NP. And dividing, we get 7.5. If you want to follow the steps of the book, they say multiply both sides by 3. So we're going to have 3 times 5/2 and 3 times the NP over 3, where that NP is going to cancel out. Either way, you're still going to get 7.5. So on the next page, you guys need to do your turn 5 and 6 here. Take a pause in the video and take some time to find the missing lengths, DG and RN, in those two problems using the triangle proportionality theorem. Alright, hopefully you've solved those your turns after you've taken a little pause here. We're going to move on and go to page 635 next. So we are looking at applying the converse of the triangle proportionality theorem. And I'll just remind you that converse, remember, means that the logic is now going to be traveling in the opposite direction as what we had before. So where we knew that the sides were parallel, or that the parts of the triangle were parallel, and therefore it divided them proportionally, we're now making the logic go the other direction, which means we know about lengths to begin with, and we're asking if they're proportional, then we can conclude that the line segments are parallel. So for example, for part A, notice the process that they go through. We want to prove that MN is parallel to KL. We do not have those markings to begin with. So what we want to know is, are the sides divided proportionally? So we have MJ is 42 and MK is 21, and that ratio does come out to be 2. So if we simplify JN over NL, the right-hand side of the triangle there, 30 to 15, also comes out to be 2. So because those two sides are divided proportionally, we can say, yes, MN and KL are parallel. Working through the same exact part there on part B, or same process for part B there, we're going to fill in what we don't yet know. They're telling us this to begin with as a given, that AC, the whole length of that side, is 36, and the whole length of BC is 27. So if I were you, what I would do is to do a quick subtraction and figure out what the missing parts of the sides are, because remember, our triangle proportionality theorem deals with parts, not the whole length. So we're going to go with 36 minus 20 is 16, and to find BE, we're going to take BC minus the EC that we know, And so that's 27 minus 15, and we get 12. Now we need to check out the ratios themselves. CD is 20, and DA is 16. And if we reduce that fraction, both having a factor of 4, we get 5 over 4. And if we do CE, which is 15, divided by EB, which is 12, both of those having a factor of 3, we also get 5/4. So, since CD over DA does equal CE over EB, then yes, we can conclude that DE and AB are parallel. And remember, the reason there is what we're talking about, the converse of your triangle proportionality theorem. So the next your turn you need to do is number 9 right at the bottom of the page here, and I'll see you guys in the next video.